In this lecture, we're going to look at special right triangles. And those special right triangles are 45, 45, 90 triangles, where two angles in the triangle are 45 degrees, and then our right angle is 90, and 30, 60, 90 triangles, where we have a right triangle with its right angle of 90 degrees, and the other two angles are 30 degrees and 60 degrees. These triangles have special relationships between the sizes of the sides that we can always count on. So let's go ahead and look at the 45, 45, 90 triangles first. 45, 40, 90 triangles are a little bit easier to memorize and understand how they work if we use the Pythagorean theorem. We're going to assume that, or just set our two shorter sides as a value of x. So this is side A, this is side B, this is side C. Then we set up the Pythagorean theorem of c squared equals a squared plus b squared. And in this case, both a and b are equal to x, so we can just substitute in x squared for both of those. We have x squared plus another x squared, so we end up with 2x squared. So now we have c squared equals 2x squared. Then we take the square root of both sides, so we end up with c by itself on the left, and on the right we end up with 2x squared in a square root sign. Because we have x squared in the square root sign, it means we can take one x outside of that radical, and we're left with c equals x times the square root of 2. So that's why up here we've written x times the square root of 2 as the length of the hypotenuse in a 45, 45, 90 triangle. So let's go ahead and look at how we can use that in some problems, but just so that I have the information I need when I'm doing my problems, I'm going to go ahead and draw my 45, 45, 90 triangle down here. So if I have side x, here's my right angle, my hypotenuse equals x times the square root of 2, and I'm just going to mark that these are 45 degrees. It's a little bit of a sloppy diagram, but it'll get us what we need when we're doing these problems down below. I'm going to get this out of the middle of our screen. Here we go. Okay, so our first problem, we are looking at a 45, 45, 90 triangle. We know that because we have the right angle, which is 90, and then we have this 45 degree angle marked. So that means we know that our other angle is also 45 degrees. If this side is 14, then it means this side is 14. But what we really want to find is x. So we know that x is the hypotenuse, and the hypotenuse in a 45, 45, 90 triangle is the length of a shorter side. So here I'm just going to write s. I'm going to rewrite this as s times the square root of 2. I'm going to write this as s, and this is s. So s is the length of the sides. And I'm just redoing that with s's so that it's easier for me to work on my equation over here that has an x. So in this case, x is going to equal s times the square root of 2, and s equals 14. So x equals, very simply, 14 times the square root of 2. So we don't even have to plug that into a calculator or really do any additional math with that. Our next example is a little bit harder because our side length has a radical in it. Again, we're going to have the same thing where x, because that's our hypotenuse, is going to be equal to s times the square root of 2. S equals 5 times the square root of 2. So that means x is going to equal 5 times the square root of 2 times the square root of 2. And when I have square root of 2 multiplied by a square root of 2, my square roots drop out. One of my 2's drops out. So it just ends up being x equals 5 times 2. So in this case, x equals 10. Now both of those examples used a side to find the hypotenuse. I'm going to go ahead and put the recording on pause for a minute, grab one more example, and put that up on our screen. So we're back, and I'm sorry that your screen just took a giant jump. So while we were on pause, I grabbed a new problem for us, and I just rewrote our little diagram for the 45, 45, 90 so we can reference it again. So here I have my hypotenuse, because it's across from the right angle, so that means this is s times the square root of 2. My shorter sides are both s and s. So if I'm trying to find shorter side, I need to find out what s equals. Well, I already said that this 210 equals s times the square root of 2, and that's really all that I need for my equation. Equals s times the square root of 2. So now to get s by itself, I have to divide both sides by the square root of 2. So s is going to equal 210 divided by the square root of 2. But I can never have a radical on the bottom of a fraction, so I'm going to multiply both the top and the bottom by the square root of 2 over the square root of 2. So what that leaves me with is s equals 210 times the square root of 2 over 2. 2 will go into 210 evenly, leaving me with 105. So s equals 105 times the square root of 2. And that's my answer. I can leave it in that form. I don't need to put it in my calculator. Alright, so now we're going to move on to 30, 60, 90 triangles. Let's go ahead and scroll down. 30, 60, 90 triangles are not quite as clean and easy to derive. So the example here that we're given, as I find my pen, here we go, is a triangle where I'm looking for side A. My shortest side, which is across from my 30-degree angle, is called x. My hypotenuse is twice that length at 2x. So I want to try and find out what A is. So again, I can use the Pythagorean theorem. So A squared, it says equals 2x squared minus x squared. Well, they kind of already went ahead of us a little bit. I'm going to go ahead and set up 2x squared equals a squared plus x squared. Now to get my a by itself, I have to subtract x squared from both sides. So I end up getting a squared equals 2x, quantity squared, minus x squared. So they skipped these steps and just went right ahead and wrote what we just found. So now they do some algebra. First we square the 2x, so we get 4x squared. And then we have 4x squared, and we have a negative 1x squared. So we can combine those because they're like terms, and we end up with 3x squared. 3x squared is equal to a squared, so we have to take the square root of both sides. So we get a equals the square root of 3 times x squared. And because that x is squared and we have the square root of it, we can just take 1x right outside of that radical, and we get a equals the square root of x times 3. So here's our diagram that shows this. And another way that it might be helpful to write this, I'm going to call this short side L. I'm going to call this 2L, And I'm going to call this L times the square root of 3. And again, I'm just giving them different names because when I work on my problems, I'm going to be asked to find side x. So, once again, I rewrote that down here so that we could look at it in relation to our problems. So 2L, L times the square root of 3. So over here is our first 30, 60, 90 triangle, and we're being asked to find two different sides. So we have 9. Our 9 is across from our 30-degree angle. So if we reference our formula diagram, across from the 30-degree angle is L. So I'm going to say 9 equals L. Y is going to be across from my 60-degree angle. So here's my 60-degree angle. That means Y equals L times the square root of 3. And since L is 9, Y equals 9 times the square root of 3. And then finally, I'm going to look at my X. X is my hypotenuse. And over here, my hypotenuse is 2 times L. So X equals 2 times L. L is 9, so X equals 2 times 9, and X equals 18. Let's look at another example. This time we're given the hypotenuse. Our hypotenuse, when we look at our diagram, is 2L. So 2L equals 4 times the square root of 3. So I'm going to go ahead and solve for L really quickly. So I'm just going to divide both sides by 2. I'm left with 2 times the square root of 3 is what L is. Now I look at Y. Y happens to be opposite my 30-degree angle. So that means opposite my 30-degree angle is L. So Y equals L, which equals 2 times the square root of 3. And then my X is my side opposite the 60-degree angle. So opposite the 60-degree angle is L times the square root of 3. So X equals L times the square root of 3. L is 2 times the square root of 3. So X equals 2 times the square root of 3 for L times the square root of 3. When I have the square root of 3 times the square root of 3, it just turns into 3. So X equals 2 times 3, which equals 6. Let's go ahead and look at one last problem that's going to be a little bit harder. We've got a story problem. Once again, I've got this goofy thing that I'm going to make go away. Here we go. So we have Kim and Yolanda are watching a movie in a movie theater. Yolanda is sitting X feet from the screen. So I'm just going to put a Y here because that's where Yolanda is sitting. Kim is 15 feet behind Yolanda, so I'm going to put a K here. This is my screen. And then I have some more information down here. It says the angle that Kim's line of sight, it should be makes to the top of the screen, makes with the horizontal is 30 degrees. The angle that Yolanda's line of sight to the top of the screen makes with the horizontal is 45 degrees. So you can see that those are shown for us there. We've got a 45 degree and 30 degree. We know that the screen is going to come down at a right angle. So now we have a 45, 45, 90 triangle. And we have a 30, 60, 90 triangle. So this whole big angle here is 60 degrees. This smaller angle is 45 degrees. So I know I'm not going to end up using this tiny triangle right here at all, because it doesn't have a 90-degree angle, nor does it have a 60-degree angle. So now I think we filled in most of the information we know. So our first question is, how high is the top of the screen in terms of x? Well, we've got a 45, 45, 90 triangle, which means if this side is opposite of 45 and it's x, this side is also opposite of 45, so it's also x. So very simply then, our answer is x. Let's look at our next question. It says, what is x plus 15 divided by x? So here, let's look. This whole line happens to be x plus 15. So it says, what is x plus 15 divided by x? So I have x here, and I have x here. Well, I'm thinking ahead, and I'm guessing this looks like a ratio to me. And we use ratios when we were using our trigonometric functions. So when it says, what is x plus 15 over x? Well, it looks to me, if I'm looking at my big 30, 60, 90 triangle, it looks like the x is opposite my 30, and x plus 15 is opposite my 60, but it's adjacent to this 30, so it looks like x plus 15 over x is adjacent over opposite. Well, that was a nice thought, but that doesn't work with our SOHCAHTOA. That doesn't fit any of our SOHCAHTOA answers. So that's not our option. So let's go ahead back to our 30, 60, 90 triangles. I'll go ahead and scroll back up so we can look at those again. With our 30, 60, 90 triangle, our short side is L, our hypotenuse is 2L, and our side opposite 60 degrees is L times the square root of 3. I'm going to go ahead and copy that and just go ahead and bring it down here for us to reference, if it will let me. Alright, so popped down everything a little bit. I'm going to erase these so I can give myself some more room. And we're just doing a little housekeeping so we can get our information closer together and see what we're doing. Okay, so now if I'm looking at my 30, 60, 90 triangle, I've got 30 here, and what's opposite it is x. Well, that's nice because that's how my diagram here works. I have 30, and what's opposite it is x. And then I have x plus 15 here, which is opposite my 60 degrees. So opposite my 60 degrees is x times the square root of 3. So I'm just going to go ahead and write that down, that x times the square root of 3 is also, based on this diagram, going to be equal to x plus 15. So again, we'll review that. In our pattern for 30, 60, 90 triangles, we have our 60-degree angle, and the side opposite our 60-degree angle is x times the square root of 3. So we wrote that here. This is our side opposite the 60. Then we'll look at our diagram. This whole big angle here is our 60-degree angle. The side opposite our 60-degree angle is x plus 15. So that's why we can set up this formula. x times the square root of 3 equals x plus 15. So then here, when we're asked, what is x plus 15 over x, we can find out they're not asking us to use SOHCAHTOA, they're asking us to rewrite that equation. So that's going to be equal to, again we said x plus 15 is equal to x times the square root of 3 over x. Those cancel out, so it ends up being the square root of 3. That's our answer for there. Alright, and then our last question is, how far is Yolanda from the screen? So even though I scrolled down, let's scroll back up and look at our diagram. If we remember, Yolanda is x feet from the screen. So we're actually going to go back to the equation we just used here for part B. And in part B, sorry for that noise there. In part B, we found out that x plus 15 over x equaled the square root of 3. So now I can actually solve for x. So if I start moving x's over by the square root of 3, I'm actually going to have a harder time getting x by itself. So what I'm going to do is I'm going to split this side up into two separate fractions of x over x plus 15 over x equals the square root of 3. Well, anything over itself equals 1. So x over x I can turn into 1. Now I'm left with just one x to deal with. So I'm going to rewrite my equation over here where I've got a little bit more space. So now I have 1 plus 15 over x equals the square root of 3. So 15 over x equals the square root of 3 minus 1. 15 equals x times the square root of 3 minus 1. So x equals 15 divided by the quantity of the square root of 3 minus 1. So let's go ahead and put that into our calculator, which has gone away. Let's get a new calculator. So I'm going to take the square root of 3, I'm going to subtract 1, and it equals 0.73205. I'm going to go ahead and copy that because I'm going to need it again. So then I have 15 on my top. I'm going to divide it by the answer we got for the square root of 3 minus 1. So divided by, I'm going to paste in that number, hit equals, and get 20.49. So we'll go ahead and round that, and we get x equals 20.5. All from just that one tiny piece of information. So that was a pretty complicated problem for using both our 30-60-90 and our 45-45-90 triangles. And happily, none on the test are going to be that hard, but I hope that was helpful to see how we can really do a lot with just a little bit of information when we have our standard formulas for the relationships of sides in our special right triangles.